What we've learned so far within this session, how to illuminate our object scene with the sphere line lights from Mr. Diener, and if sensors and electronics are available in the near future, we also got information about what kind of sensors we can use in the sphere wavelength range to acquire our multi-hyperspectral images. And now, our colleague Pavel Paclik, CEO from perClass, brings together how to interpret the data, how to calculate on the data, and how to make the hyperspectral images available for industrial applications. So, our next speaker is Pavel Paclik from perClass, and he will speak about end-to-end workflow for hyperspectral object sorting with their perClass Mira software suite. Pavel, the stage is yours.
Thank you very much for the introduction. I'm very happy to be here and show you the progress that we made in the last few years since the last vision in the software tools for actually solving practical problems with spectral imaging in sorting applications. In my talk, I will first make a little bit intro. Why do we actually go into spectral imaging? And then I would like to show you workflows for object classification and object quality estimation until deployment. So how can you actually build in steps your, let's say, next intelligent sorting machine? A little bit about perClass. We are a Dutch company. We have now more than 15 years of experience in industrial machine learning, building algorithms, and deploying algorithms in industrial setting. We have gradually focused on multi-band spectral imaging, and in 2018 we brought a specific product for this market that is called perClass Mira, which is the easiest user interface for interpretation of spectral images with real-time deployment. So, typical user of perClass Mira is a system integrator or applied researcher that can really analyze the data, can extract information from spectral images, either for batch processing or, like in this presentation, for real-time online applications. So final goal is to deploy the models. So what is spectral imaging? We are looking at complicated data cubes where for each pixel we have complex signal looking at the typically reflected light from the sample. So there is a lot of information, typically like 200 channels in a hyperspectral image. We have this very rich information about the properties of the material, so we can actually look at sort of material sensing or looking at quality of objects. But why should we actually do it? Can we give some simple examples? So if I look at potato chips on a tray, and I image it with a classical color camera, and I also look at a single band from a hyperspectral cube, you don't really see something very exciting. But if you look at the entire cube, we can use some clever statistical algorithms to actually extract information, for example, about the internal defects or defects on the surface of the objects, but defects such as greening that are actually not yet visible on the sample itself to the naked human eye or to the classical vision with color camera. So that is the exciting thing, that we can basically look at defects that are otherwise invisible to us and look even at the quality of products. The major challenge is, of course, how do you get from the cube to this application-specific interpretation? And that's where perClass is stepping in. So we provide software tools where the system integrator, let's say, can address these many questions that are between a sensor and an application. There are different types of interpretation, and in typical sorting application, we see these two first types, so classification and estimation. So let me just focus on the classification first. In these kind of use cases, you want to classify materials. You want to find defects. You want to find and identify, let's say, foreign objects in your product. So how do we actually go about it? What is the workflow? The first step would be that you want to build a pixel classifier, and in perClass Mira, this means that you basically define your classes and you are free to annotate your samples, provide basically label examples that you are interested in. The software is automatically building models for you, and you can refine your solution gradually. So you can improve the labeling, get the updated models. You are completely free to define your classes as spanning multiple materials based on the logic of your application. It's not like one class is one material. you can definitely learn from many samples, many scans, and you can also use advanced tools that will guide you where the models do not know yet. So this grayish area, that's where the models did not see these kind of examples before, so you can basically precisely improve where you need the improvement. So that's the pixel classification part that is a very flexible, very quick process. You get to models that operate on individual spectra. Then the next step, you want to understand the errors. We want to know where the errors are happening and why. So there are a lot of different tools that you can now use interactively. I will just show you one that you can basically drill down to the labeling that you provided, and you can understand which of these labels are actually correctly or incorrectly handled by the classifier, so correctly in green, incorrectly in red. That often gives you the insight. You understand that sometimes you make labeling errors, sometimes you have basically unrepresented things in your data, and we think that really the understanding and the interactivity is helping you to make better solutions. Once we have the solution at the pixel level, we want to move to the object level, and that means that we basically say which classes are interesting for us. We can get the objects segmented, remove small objects that are typically not really interesting, and you can directly work with multiple foreground or important classes that are also segmented separately, so the touching objects are handled properly. In the end, you are basically getting the per object information, coordinates, sizes, bounding boxes, and decisions. So this is information that your sorting machine can use at runtime to actually perform some action. This use case is where one object is one material or one class, and that's quite common for a kind of detection scenario, but often we are looking at grading solutions. Back to this potato chip example, you are looking at the defects in the potato chips, and once we map them on the pixel level, of course, the object segmentation also provides then the extra information on the content. So you can sort by content of the object, by the size or fraction. Another example that I would give here is unknown foreign object detection. This example was done with Kubert Ultris camera, so not a line scan like what we saw in the previous examples, but it's a snapshot camera, so in each readout you get a full spectral cube. The interesting thing here is that we trained on the product, on the minced meat and on the belt, but not on the objects themselves. So here we have an example of an application where we are detecting the objects that were of any material that is not trained, not part of the training process. Let's say that we have a classifier, we have some solution, in this case lentils with near camera, we have per pixel decisions, we have object segmentation and object decisions. The logical next step that sorting projects really need is performance, an understanding of performance at the object level. That's what you can do now. You can annotate your objects, you can get the ground truth basically quickly created, and then we can compare that to the real decisions of the system, and again, interactively basically look and drill down of what is really happening. So what we see on the right side is a confusion matrix comparing the truth that we know, the ground truth, and the decisions, and we can really drill down and understand what are the errors, where are they happening, and that often leads to improvement of the system. It's even more important to understand what ground truth objects or what regions we don't find, so you should not miss. And also other way around, looking into the decisions, drilling down on real decisions of the system. These are decisions that are matching the ground truth. More importantly, often is to look at false positives, decisions that are actually not matching, because that's often a really, really critical thing to deal with correctly. So this was on the level of a single image, because it's very interactive and quick to get insights. But of course, in larger sorting projects, we need to go over many scans, often hundreds of scans. This is an example from an application with 11 classes. You are looking at a confusion matrix on the object level, so there is like almost 600 objects to get really insights on the true performance for the sorting machine. So that was the classification use case. The estimation use case is basically going a step further. We want, for objects that we find, we actually want to estimate some quality parameters, such as sugar content, fat content in meat, protein content in product, and so on. So how does that actually work? Let me first show you examples of projects that can be accomplished with this technology. So first one is tomato Brix and acidity estimation. Brix and acidity are important because with these two parameters you basically characterize the taste of a tomato. Taste is not a single dimensional concept, but at least you need 2 dimensions. And we can here estimate for new tomatoes basically these 2 parameters. Another interesting example comes from Hedwall Photonics, where they have a project looking at bricks in oranges. What is really special is that they are really looking at the truck level, truck coming to the facility. In the past, very time-consuming process of getting some sample from the truck, measuring the bricks in the lab, and basically with a time delay, finding out where the truck should go in processing. So now Hedwall is optimizing this process with a hyperspectral camera, and the results that you can see on the plot are on the truck level. So these dots are trucks coming in, the green ones are unseen in the process of the design. And you can also see the sensor that is handling this application. That's the Hedwall MVX that you can see here on the fair live. And the interesting thing about it is that it's not just the camera, but also the processing unit. So in these kind of applications, you will be actually able to get the per truck bricks estimate directly from the camera without additional computing hardware used. Another interesting application is looking at the baking time estimation in the oven, made with Resonon camera and Laser 2000 support. And here we are basically estimating this time on the object level on the graph. And then if we have the good model, we can actually map it back on the pixel level and get some insights how this process is actually happening. So often this pixel visualization gives us very interesting insight on your sample, and that's really very nice for spectral imaging, right? Classical point spectroscopy can give you one measurement, but here we can see distribution in your sample. Another example highlighting that with Cilios camera of 8 channels, you can also build in certain applications estimation models that are good enough. In this case, it was estimation of mixing proportions of certain material. So there are a number of options, a number of interesting opportunities here. What is the workflow? If I look at this example with tomatoes, we want to start with a pixel classifier. We want to learn what is a good surface of a tomato. We want to exclude reflections. We want to exclude, let's say, defects. We turn it basically to objects. And then we are annotating these objects with the extra metadata about, let's say, Brix, acidity, and other kind of parameters. You can do it manually, but typically your workflow is that you scan the fruit and then you do the destructive lab measurement. So you get a large document, let's say in Excel, collecting a lot of results. You can annotate in a batch, importing all this information in the software and build your regression models, because often you really need large numbers of objects. Once we do that, we can apply it to any kind of scan where the whole pipeline is running, including the object detection and per object estimation thing. So I would like to show you a little bit a few examples from larger projects. We need to scale to large data sets. Here is an example of 219 scans, which depending on the sensor can be a lot of data, in this case 13 gigabytes. We are estimating the dry matter content in leaves, so it's a plant phenotyping application, and it's a very large data set. So things often can take a long time. Here we want to test what happens if we have 20% of our images as testing only, and the responses of the software need to be quick, because you need to make the next decision, what do I do? So I would like to demonstrate that, of course, once you need to go through these large data sets, but once you do it, you have a very fast turnaround and you can work with very large sets and problems. Very important part in especially estimation projects is about data cleaning. Here is an example about outlier detection, basically samples that are far away from the domain where your model was trained, and we provide now tools to identify outliers. The important thing here is that this outlier scoring is not using your ground truth. So you can also run it actually in the deployment mode, which is very interesting for fruit sorting applications, to identify that there is maybe a variety of fruit that was never trained, and you should better change the model or stop the machine. Another example, if looking at error plots, you can spot, for example, systematic errors. They can be unseen varieties, there can be different conditions, but it's all about basically understanding where problems happen, drill down to these examples, to the metadata that you have to build better systems. So that brings me to the deployment side. We support a number of cameras. Typically, you have some vendor SDKs to read data from the camera, or you have standard compliant solutions like Genicam. You pass the raw data from, let's say, the line scan camera to the perClass Mira runtime. All steps, so correction, pixel, object classification, is happening in the runtime, and you just read out the coordinates, decisions, or object quality measures that you computed, and you can drive your actuator. System integrators, of course, immediately ask us, is it fast enough? This is a really important question for them, so we actually, for supported cameras, enable direct testing of the speed of the whole solution from the user interface. You can see it on our booth, and here are some examples from non-trivial sorting application with a SpecIm FX17 camera, with PC hardware and embedded system, NVIDIA Jetson. So you can get full frame rate using all the data from the spectral camera for non-trivial sorting task. You don't need to do integration yourself. You can currently already get some hardware integrated, again, like the MVX system from Headwall that is embedding the processing unit and perClass Mira runtime. So that gives you really much faster integration. Another example and another way how to approach deployment is with Pleura AI Gateway, so embedded computers where you can work with any Genicam compliant hardware, and you can also do customization and plugins, Python scripting on the unit itself that helps you to quickly customize the solution. Here we had an example with coating defects in pills. That brings me to conclusions. I would like to stress here that today system integrators with spectral imaging can really end-to-end design their systems without programming. It's actually a huge step from a few years back. It's really speeding up things. You can now do workflows both for sorting and for quality estimation. You are able to get the performance and understanding of performance at the object level, which is really important, and you can deploy to online hardware or integrated solutions at high speed. So if you have any questions, happy to answer, and or welcome you on our stand where we have live demos of bricks estimation and sorting. Okay, thank you very much.
Okay. Thank you, Mr. Paclik, for the nice presentation. Also for putting together, again, these great practical examples. And in fact, you've shown that perClass is a software which is working with many of the major players in spectral imaging concerning the hardware. Mm-hmm. So for me, that was, again, really impressive to see where the software is working and how. We will now go over to the question and answer part. And first question is, can you give a short recommendation concerning hardware setup? Because you mentioned some slides before. What is necessary to run the software and to bring it into the field? Okay, it's nothing special. We really target users such as a biologist with a laptop, so you don't need a workstation. Of course, you can take advantage of a GPU, and it's really useful, especially if you have hyperspectral cubes, a lot of data. It's speeding up the process. But you can just use basically any PC with Windows, and of course sufficient memory is good, but that depends on your sensor. So okay, that's not special recommendation. But a high-performing graphics card with GPU will improve the whole It's an thing. Optional thing. It speeds up processing. Okay. And last question to stay in time. What about color imaging calculation and color image processing? Because if you have the advantage in the visible wavelength, color is also a thing you can calculate from full spectral information and can also be used to differentiate and to classify it. What about these functionalities? Yeah. Currently, we do not support it in the software, but we actually internally are working on these kind of solutions because we see demand from the market. So if you have an interesting application, please come, because there are very interesting sensors available now that can address, let's say, color constancy and similar kind of applications. So please give us the feedback. We are implementing the functionality that people really need and are willing to pay for. That's basically our major drive. Okay, thanks again. Thank you. To the audience, thanks for joining the session, the hyperspectral sessions, and We hope you enjoyed, and stay tuned here at the Industrial Vision Days. After us, the next session is coming. So, bye-bye.